In the first year, I taught you about hardware, the body of the computer. In the second year, I've taught you about software, the mind of the computer. In the third year, I'm going to teach you about logic and computation, the spirit of the computer. This module is going to cover some of the philosophical and mathematical ideas underlying the very foundations of computer science, which I've alluded to occasionally in my other modules. Dijkstra said, computer science is no more about computers than astronomy is about telescopes. This means we won't be studying particular computers, particular machines anymore, but we're going to study the spirit of computation itself. What is computation? What does it mean to compute something? What are the limits of computation? Are there things that cannot be computed? We've already encountered some forms of logic. We began with Aristotle. Here's a logical inference called a sequence. We say for all x, if x is a human, then x is mortal. If we're given that, and we're given that Socrates is a human, we can conclude that Socrates is a mortal. Aristotle didn't use this notation. The idea of generalizing over all x and also asking questions about existence, does there exist an x, was introduced much later by Frege. In modern logic, we'll see the use both of these upside down a's and these backwards e's to represent all of something or any of something. We can write both statements about objects in the world, humans and Socrates, but also statements about mathematical objects using logical notation. Here's an example of a logical statement from mathematics, known as Fermat's last theorem. Here we're asking, do there exist numbers such that x to the power of n plus y to the power of n equals z to the power of n for n greater than 2? Now, in the case of Socrates being mortal, this is quite a simple inference, and you could imagine building an AI system which could operate on these logical structures, perform computation on them, and draw conclusions. That's the aim of classical AI, to draw target inferences from input logical facts. When you're given something like Fermat's last theorem, this obviously is a very difficult theorem. It has now been proved by humans, but it took many years to do that. And this asks a question about the limits of computation and the limits of AI. Is it possible for a program to exist which could take a candidate theorem like this as an input and tell us whether the theorem is true or false? If we could do that, we'd have a very powerful machine which could draw any true conclusions from any set of input axioms. Logic progressed from Aristotle through Frege. We've already mentioned George Boole and Shannon's digitization of Boolean logic. But a revolution in logic occurred when Kurt Gödel began to ask questions about the fundamental limitations of logic and computation. Gödel wanted to know, are there theorems like this which cannot be answered by an algorithm? I'll give a brief sketch of Gödel's proof here. This is only a sketch, a cartoon. Come and do the module to see the real thing. It draws on several ideas we've already seen, beginning with Gödel numbering. In computer architecture, we discussed how any string written in, say, ASCII code can be considered as a number in, say, base 256. Every ASCII character can be written as an individual number between 0 and 255. Consider a whole string of ASCII characters, each character in that string as being a multiple of a power of 256. So for example, take the string representation of this function definition, lambda ab, which returns a plus b multiplied by a to the power of b. This is a string. It may represent computation, a function, but we can also consider it purely as an ASCII string, assuming we have a symbol for lambda. Let's assume lambda is represented by ASCII 255. We can write this string out. We'll see that the bracket is the number 40, that's in position 21. The lambda is the number 255, that's in position 20. The letter A, the third character in the string, is number 97, that's in position 19. By writing it first as a string, then converting it into a base 256 representation, we can consider any program to be mapped to a single integer. These numbers will be very large. It's common in computer science to consider data as large numbers. For example, a piece of data such as an image could similarly be written as a very large integer. If we consider every pixel in an image in this way, For example, if we have 256 shades of grey, every pixel in that image will be a multiple of a power of 256. We add them all up together and we have a large number. Any string can be considered as a large number in this way. Some integers are illegal to know. Some integers can be considered as representations of things like copyrighted programs, of child pornography, of cryptographic keys. You can be put in prison for knowing some of these numbers. But here we're considering the Gödel number of an arbitrary program. By writing a program as a single integer, we make it amenable to doing mathematics upon. We're good at doing mathematics on integers. It's hard to do mathematics on programs. But by converting programs to integers, we bring them into the realm of inputs to our functions. Let's consider we write a program that computes whether a theorem is true. We can write a theorem as an integer using Gödel numbering. This means we can create a function. Let's call it prove it. And prove it is going to take initially a string representation of the program. It could convert that to a single integer, and it's going to return a bool. And the bool is going to tell us whether or not the theorem is true or false. This is now a apparently simple mathematical function. It takes effectively an integer as an input and it maps integers to Boolean. But think about what this means. If this function really did exist, we could, for example, call it with arbitrary theorems, such as Fermat's last theorem, and expect it to tell us the answer. This would form a universal AI. This would be able to answer any question. Gödel was concerned about this idea. It would in particular have meant the end of mathematics because the whole subject could have been automated. You could run your computer program, give it a theorem, it would tell you is it true or false. Gödel's research found a way to show that this program can never exist. Here's a sketch of how the theorem works. We begin by assuming we have such a function. The function prove it takes a string theorem as input and it returns a Boolean. Is this theorem true or false? Consider a new class of theorems or programs. This is a Gödel function taking integer n as an argument. And this function says for input n, that's the lambda, if prove it n is true, then return false, and otherwise return true. What this function does, it calls out to our God function, our universal AI, which tells us if the theorem is true or false, and then it returns the opposite answer. Now we can encode this function itself as an integer using Gödel numbering. We're going to take the definition of the Gödel function and we're going to turn it into an int. Now consider the special case of calling Gödel's function on itself. The function Gödel has been encoded as integer g. We're going to consider calling Gödel on integer g. What is the value of this? If Gödel of g is true, then from the definition of the Gödel function, Gödel of g must be false. That's because we've called prove it to ask whether the thing is true or not, and we've deliberately returned the opposite truth value. Conversely, if Gödel of g is false, then Gödel of g must be true, again following from the definition. What Gödel did was create a logical version of the sentence, this sentence is false. It's a classic logical paradox. I enjoy telling you guys that all lecturers are liars. I always tell you this because you shouldn't believe anything you hear in a lecture theatre. Of course, I really know this is a self-contradictory sentence. This is a English language version of the logic underlying Gödel's theorem. Gödel's proof began by assuming the existence of the universal AI, the universal prove it function. And we've derived something which appears to be a contradiction. We found that if Gödel of g is true, then it is false. And if it's false, then it's true. This suggests that there is therefore no universal AI program. Gödel's theorem is related to Church and Turing's work, which converted it from a logical form into computational form. You can, for example, consider a program which tries to determine whether another program will ever halt or not. And you can create a programmatic analog of Gödel's function which says if a program terminates, then go into an infinite loop. And if a program does not terminate, then stop. And as in Gödel's theorem, you can then call that program with itself as an input to create a contradiction. Understanding the meaning of Gödel's theorem is beyond the scope of this overview, but variously interpreted as showing there is a difference between a statement being provable and it being true, which is catastrophic. If your notion of mathematics and logic defines truth as provability, then you have a problem, because now truth seems to be something else, which is really out there, even though your logic is not able to define it or prove it. Why study logic and computation? Some of this stuff sounds pretty esoteric, and it is, but it is also deeply beautiful. You will come across these ideas running all through computer science. You will often come across a problem which opens up a huge rabbit hole, and you have to decide, do you want to go there, or do you want to run away from it? You'll come across statements that are neither true or false, or both. You'll come across the fact that you can never be sure if two numbers are equal. How do you compare two numbers for equality? Alan Turing's paper on computable numbers was not really about computers. It was about numbers. What Turing really did was redefine the real number system. Using that definition, we can consider any number to be a program. And a program is a string, and a string can be represented by an integer. So to compare two numbers for equality, we have to compare their programs for equality. That means we have to test whether the two programs compute the same thing. Can you create a function which takes two programs as inputs and compares their behavior for equality? And this turns out to be an uncomputable problem. That means we can no longer tell if two numbers are equal or not. Logic and computation does have applications which involve taking programs and making deductions about them. We often need to take a program as input, for example, when we're writing a static analysis tool. How do we create programs like linters? How do we create systems that can check your program for bugs automatically? How could we check if your program will ever go into an infinite loop? But this turns out to be an uncomputable problem. Logic finds many applications at the hardware level. Going back to computer architecture, we can represent a digital logic circuit as a logical theorem. We can then take that logical theorem and we can do proofs based on it. In particular, we can prove whether its logical representation matches a desired function which we're trying to compute. We might design a circuit representing an adder and then create a proof that it really is performing addition. So there are multi-billion-dollar applications here in verifying both software and hardware. Perhaps this is how we should really do software engineering. Employability. Logic and computation is hard. It is very hard. It's likely that most students who try to study this will fail or score badly in their exam. It's a difficult course. You do it because it's beautiful and you love it and you feel the need to find the answers to some of these questions. But if you can make it through a hard subject like this, that sends a strong signal that you care about topics like this, you are interested in difficult problems, you're interested in things that are beautiful and hard. For example, I got my job in a hedge fund by spending about 2 hours discussing could a quantum field-based computing machine circumvent Gödel's theorem. You'll also find many of the ideas in logic and computation, while you don't pull them out on a daily basis as a design pattern in your code, they do inform everything we do in computer science. They provide the foundations of our thoughts. You will find many systems and ideas are ultimately based on the lambda calculus, on Turing machines, on Gödel's theorem. If you understand that language, if you understand the basis of your subject, similar to learning Latin, if you're a linguist, it will put you in a position where you can rapidly get up to speed with other systems and ideas that are also based upon them. Simple concepts such as lambda functions have come directly from the lambda calculus. We're starting to see those appear in languages like C now. This is a rabbit hole. If you want to go further down it, I'd suggest you have a look at these two books over the summer. Gödel Escherbach is a notorious, beautiful, crazy, maddening book. It changes people's lives, not always in a good way. Go and find it in the library. Metamaths. Chiton is famous for creating the number omega. Omega is the most terrifying number in the world. Every digit of omega tells you whether a Turing machine will hold. Every Turing machine that could possibly exist is an element. So if you know the number omega, you are God. You know everything. Understanding the foundations of computer science makes us better programmers, better software engineers, better members of our communities.